Okay, this is going to be our first video in our electric potential module, which is going to be the third module of this course. We're going to cover a number of different topics in this module, but let's start off with electric potential energy. So the first thing that we're going to want to do is we're going to want to recall from our Physics 111 a number of things that we already talked about in that course about potential energy, energy conservation, concepts like that, work, and so forth. So I'm going to do a quick little review here. First, we have our expression for work here. So when a force acts on a particle, causing it to displace from some point A to point B, we can see the work done in moving that particle from A to B is given by this equation here, and you guys should have seen this in your Physics 111. If it's a little rusty, I would recommend going back and taking a look at that. The textbook actually has a number of chapters, or at least one chapter, and then some review on this stuff. So go back and refresh yourself on it if it's rusty. But basically, this is our expression for work. Here this dl is an infinitesimal displacement, and phi is our angle between our force and our dl. Okay. We then, in Physics 111, would have talked about how if F is a conservative force, i.e. that if the work done by F is path independent, we can associate a potential energy to this force, to this work, and so we signify that with a U usually, or maybe a PE sometimes, depending on where you did your Physics 111 or Physics 111 equivalent. And so we end up with this expression here. We find that the work done is equal to the negative of the change in the potential energy, right? And then after we talked about that for a little while, we introduced the work energy theorem that lets us sort of connect the work done to the change in kinetic energy, where we've already discussed how this also relates to the change in potential energy. So we end up with this expression that we see here, and this allows us to write down this very useful conservation of mechanical energy equation that you would have used a bunch in your physics 111, and potentially even before that in high school, right? And this is just telling us that our initial kinetic energy plus our initial potential energy is equal to our final kinetic energy plus our final potential energy, right? And so we're going to make use of that a bunch here, but we want to have this idea sort of firmly put in our heads. Before this would have been, we would have talked about things like gravitational potential energy maybe, or spring potential energy, but now we're going to extend this to electric potential energy, okay? So keeping all that in mind, let's move on and let's discuss electric potential energy in a uniform field. And so we can kind of develop this concept of electric potential energy the same way we develop the ideas of gravitational potential energy. So we have this nice figure down here from the textbook. This is 23.2 from the text. And if you just imagine that this was the ground, okay, and these electric field lines, they were just our lines of the direction in which gravity is acting on our particle, and this Q naught here, instead of being some charged particle, was just some particle with mass. This F would end up being the gravitational force, right? Not the electric force that we see here, and the whole thing would kind of come together the same way. But here we're going to be developing it with the electric field in mind. So here we have two charged plates. We have a positively charged plate on top and a negatively charged plate on the bottom. This sets up a uniform electric field. In this uniform electric field, we have a test charge Q naught here. It's experiencing some force downward, right? because our Q naught is positive. We set up some distance here, y. This is our distance from the bottom plate here, which is where we're considering our zero potential, right? This would be no potential energy at that point, and we'll talk more about that in a minute here. And if we set up this distance here to be d, we can kind of sort of build up these ideas. So let's keep looking at this here. So we know that in a uniform electric field, maybe I should keep the drawing on screen. So we know that in a uniform electric field, our test charge is going to experience force given by this equation here, right? And so because we're in this uniform electric field, we don't really have to worry about the electric field changing from point to point, right? So in principle, we would have to do this integral that we see here, that the work done in moving from A to B is equal to the integral from A to B of F dot dl. But because F is not changing anywhere, because this is a uniform electric field, this reduces down to just FD, right? Because our F will come out of the integral, and we just have to do the line integral of dl from A to B. But if we're doing the line integral of dl from A to B, that's just d, right? We're just breaking this up into a bunch of tiny little segments and then integrating over the whole thing, and there's nothing else that's in the integral, so it's just going to give us back that length that we're integrating over, right? And so we end up with this expression that we see here, but we can just substitute in for our f in terms of this equation that we have up here. So we end up with the work done in moving the particle from A to B is just equal to the charge on our test charge times the magnitude of the electric field times the distance over which we're moving it, right? Okay, so the work done here depends only on the initial and final y components of the particle, right? So this is our d here, or our y, depending on where we place it, right? This is very, very similar to what we found in the case of gravity, right? In the case of gravity, all that mattered was our height, right? It didn't matter if we were if we moved a thing from the left to the right. All that mattered was if we moved it up and down in this gravitational field, right? As our h increases, our potential gravitational energy increases, and so we're storing more energy as we're lifting something up. But if we move it left and right, it doesn't really change its potential energy, right? And so the same thing happens here. Here we're basically replacing our m for our charge. So in a gravitational field, it's the mass of the object that matters. Here it's the charge of the object. Our g is replaced with our e, the magnitude of our electric field, and our h is replaced with our d, right? So before we were concerned about height, now we're concerned about distance, right? But basically the same ideas. And so this allows us to write down our work again in the way we would have seen before and above, but now we're just going to replace the u's for these expressions that we've developed up here, and this sort of strongly suggests a way in which that we can write down our electric potential energy in the form that we see here. Okay, so maybe I should have boxed this one off, or maybe I do below. Do I? I don't think that I do. Okay, so anyway, this one should probably have a box. This is a pretty important equation, and so this wouldn't always have to be a y, right? It would depend on how we set up our coordinate system. So this could be any sort of coordinate, but it only really matters. It only really depends on the distance away from or in this electric field that our particle is, right? And so we're going to find that in this case, like I mentioned above, we've set u equals 0 at y equals 0. We've set our zero potential at this point here. But it's really only the change in potential energy that matters, right? And so we could choose any other point as our zero potential. For these types of problems, we're going to find that oftentimes it's useful to set infinity as our zero potential. But in other problems, let's say in chapter 25, that's going to be coming up in a couple of chapters, we'll make other choices. So it really depends on the problem that we're trying to solve. But we'll see a couple of examples of this coming up, and we'll see how it sort of plays out. Okay, so the textbook had some nice diagrams here of how our U increases or decreases depending on whether the charge is positive or negative in our electric field. But you can always just imagine it in analogy to gravity, right? So if you're lifting something up and you're working against gravity, you're increasing this thing's potential energy, right? And if you lower it back down, it has less potential energy. And that's the same idea here, except that here, well, in gravity we only had mass, right? So there's only positive mass. But here we have positive and negative charges. So if you have a negative charge, it just flips everything, right? So as you can see in this diagram here, this thing will have a lower potential energy. If the charge is negative, it'll have a lower potential energy when this object is further down here, because our electric field is pointing downward and our charge is negative. The further down we go, the higher the potential energy, and the closer to the top plate it gets, the lower its potential energy will be, because its tendency, the force on it is to move it in the direction of the positive plate, right? And so it just flips the whole thing by a sign. Okay, so that's what those 4 diagrams are about there. And right, so I guess what I write here is another way to think about it. So another way to think about it is that U increases if Q, like our test charge, moves in the direction opposite to the force it's experiencing, right? So if you're moving it against the force that it's experiencing, your potential energy is going up. Okay. Okay. So now let's take a look at the electric potential energy of 2-point charges. Okay. So we just looked at our test charge in a uniform electric field, but now let's look at it in a not uniform electric field. 2-point charges. If you have 2-point charges, you have 1-point charge here. Let's say, or maybe I should draw it like this. This is a positive. Let's say the electric field is going to be something like this, right? And it'll be increasing as you're getting farther away. So it's not uniform. If you put another positive charge here, this thing is not going to be in a uniform electric field. So now you can't just sort of ignore the integral that we skipped over before, right? So you end up with a force, and maybe I should show you guys the equation again. So we did this integral here, right? But we were able to just pull out this force because it was uniform. It had no dependence on our position, right? But here, this is not a uniform field when we're dealing with 2-point charges. This is what it looks like, and it has our dependence. It matters how far away these particles are. So we can't just pull it out of the integral. So what do we end up with? Well, we end up with basically this. This is our F dot dl. Except that F and dl are going to point in the same direction, right? So dl just becomes dr, right? That's going to be our distance, our radius from 1-point charge to the other. That's going to be our r. And so we're going to be integrating over tiny amounts of that, right? And our force is this expression that we have here. So as we sub the two of those in there, do the dot product, we end up with this expression that we have here. And if we do that integral, we're going to see that everything comes outside of the integral except for this 1 over r squared. We're going to do that integral and then use these two limits of integration to finish the calculation. We end up with the expression that we see here. Okay, so that's great. Except that as we're doing this, everything is happening in only the radial direction, right? We're only thinking about a particle that we're considering some distance away, r like this, but we're only considering this direction. What if we're moving this particle on some weird path through here, right? Does it matter what path we take? Well, we're going to find that it doesn't matter, that all that matters is our initial r and our final r. And I really wish I had left myself more space to draw here, but basically what I'm drawing here is what we're going to see directly below. This is this nice diagram from the text. And let's take a moment to sort of focus on this. What's sort of happening here? So we have some initial point A where our test charge was, and it's sitting in the electric field of our charge Q here. And then our test charge can be moved through whatever path we want. We can look at this path here. It can be moved to point B, or it can be moved over this path here to point B, right? And so we started off with some RA here, and in the end we end up with some RB. And we're going to find that the change in potential energy only depends on the change in this R value, only in the magnitude of our radial component here at both of these points. So it doesn't matter what path we take. In the end, all that matters is this R value at the endpoints. Okay, and so let's take a look at how that sort of plays out here. So we can see, well, as I just said, we can see that the work done here is still only dependent on the radial change in the distance. So dr is all that matters, okay? And so in this case, we can write it kind of like this. And let's remember that this phi is the angle between f and dl. But let's take a look at the diagram again. They do a nice job of illustrating this here. We can see that this phi with our dl, if we take the cosine of theta times dl, well, we just end up back with our dr, right? Like, just think about applying a cosine to our dl. Like if this is our hypotenuse, and I won't leave that there, but if this is our hypotenuse, we take the cosine of phi, and then considering that this is our hypotenuse, we end up with dr back. But that's great, because that means that we can simplify this to just dr, right? And that's exactly what we just did before. We ended up doing this integral, and we found this result here. Okay, so that's sort of a big simplification that we can make, and this shows us that the work done by the electric force, or by moving this particle through the electric field, is path independent. It only depends on our initial and our final R values. And so we are justified in assigning a potential energy to this force, because it is path independent, right? So we can write U as we see here. Okay, and I already have it boxed, so I don't know why I'm doing that, but basically we can see that our potential energy can be written down. This is our electric potential energy, and this is going to be a very useful expression for us to do calculations with in a moment here. Okay, so as I said, this is our electric potential energy. We have the expression from before of how our potential energy relates to the work done, and now we can take a look at some examples. Before I do this, let me just pause the video and save this so I don't lose any of the notes I might have made above, and then we'll get into this example. Okay, so we can get into the example now. So this is example 23.1 from the text. We're looking at conservation of energy with electric forces. And so what do we have here? Okay, so we have a positron, which is the electron's antiparticle, and we're given the mass, and we're given its charge, and then we suppose that it moves in the vicinity of an alpha particle, and well, it's not really important what it is, but basically we're given its charge and its mass, and so we're told that the alpha particle is about 7,000 times heavier than our positron, and so we're going to assume that the alpha particle is at rest, and we're going to be looking at the motion of this positron, right? So we're told that when the positron is this distance away from the alpha particle, it's moving directly away at some velocity, and we want to find what the positron's speed is when it's twice that distance away from the alpha particle. Then we want to find its speed when it's very far away from the alpha particle, so basically as the distance goes to infinity. And then we want to suppose that the initial conditions are the same, but that the moving particle is an electron, not a positron, so we're going to flip the sign on the charge and see how that sort of affects our motion. Excuse me. Okay, so let's get to it here. I don't know if I've left enough space. Maybe. Let's hope so. Okay, so I'm just going to kind of draw the setup to begin with. We have, let's call this our positron. Okay, so our positron has some charge. I won't rewrite the number, but it's, or maybe I will. Okay, and it has some mass. What is that? 911. Okay, and it is going to be some distance. Let's do a thing like this. Say it's some distance. This is our alpha particle, and our alpha particle, we're going to call this Q. This is going to have some charge, 3.2 times 10 minus 19 coulombs, and a mass much larger than that of the positron, at 6.64 times 10 to the minus 27 kilograms. Okay. So this thing is at rest. This thing has an initial velocity. It's moving off with a v 3 times 10 to the 6 meters per second. And this thing here, this is our, I'm going to call this d, capital D, is going to be 1 times 10 to the minus 10 meters. This is our initial distance between the two, okay? And so in part A, maybe I'll start doing it down here. Yeah, okay. So in part A, we want to find v when our d, and this is not the same d. This is a variable d. So we want to find it when our d is twice that d, right? So we want to find it. We want to find v when our d is equal to 2 times 10 to the minus 10 meters, which is just 2 times our capital D, right? It's just 2 of these d's. So we want to find v at that point. How are we going to do this? Well, this is going to be very, very similar to problems you would have seen in earlier physics courses, where we're just going to apply conservation of mechanical energy, right? So how do we do this? Well, we start off with conservation of mechanical energy. Initial kinetic energy plus initial potential energy is equal to final kinetic energy plus final potential energy, right? And here, our kinetic energy is still the familiar half mv squared, but the potential energy that we're talking about is electric potential energy, which is going to be given by 1 over 4 pi epsilon naught q naught over r squared. Oops, over r, sorry, definitely not r squared. Okay, and so this is good, right? I hope I didn't make that typo here. No, I didn't. Okay, good. All right, so let's just start subbing things in, right? What's this equation in terms of these variables? So what's our initial kinetic energy? Well, our initial kinetic energy is simply going to be 1/2 mv initial squared, plus what's our initial potential energy? Well, that's going to be 1 over 4 pi epsilon naught q naught over d, right? Our d from the diagram here, just our first displacement or our first distance. And what's our final kinetic energy? Well, that's going to be 1/2 mv final squared. We don't know what v final is, but this is what we want to find, right? This is the one that we're looking for. Plus our final potential energy. Well, that's going to be 1 over 4 pi epsilon naught q naught over d. Okay, and this is our lowercase d. This is the d. This is the d that we have here. This is twice big D. And so really, at this point, let's just solve this algebraically. So the textbook, if you look at the textbook, they do this example, and they right away go into numbers right away. I'm trying to pull it up here. Yeah, so they go directly into numbers right away, calculating each one of these initial kinetic energy, initial potential energy, final kinetic energy, and so forth, all explicitly right away in terms of numbers. I find it's faster to just leave it in terms of these variables and then fill them in later, because we can solve all three problems basically by doing this one calculation. So let's do it this way. You guys can look at the textbook version of it if you want to see the way they do it. But so we're basically just going to take this equation and manipulate it. We want to solve for our final velocity. Okay, and that's pretty simple. We're just going to end up finding that, well, here, we can do it in a few steps. So 1/2 mv initial squared, and I'm going to move this final potential energy over to the left here. So we're going to end up with 1 over 4 pi epsilon naught. Excuse me. With a q naught over d. This was our initial potential energy, and now we have our final potential energy, q naught over small d, and this is equal to 1/2 mv final squared, right? So now let's solve for v final squared. We're gonna multiply through by a 2 over m, and so we end up with this expression here. We're going to have v final squared is equal to v initial squared plus, and I'm going to factor some stuff out of this, we're going to end up with a q naught over 2m pi epsilon naught 1 over big D minus 1 over little d. Okay, and there may have been some skipped steps in there, but this is what you end up with in the end. Okay. Okay. I'm going to call that our star equation, and this star equation we're going to use to solve parts A, B, and C. This is kind of why it's nicer to keep it in terms of variables, so you don't have to do all those steps with all those numbers every time. Very, very sort of straightforward this way. Okay, so as far as part A goes, we're interested in d equal to 2 big D, right? We're interested in the velocity when our particle is twice as far as it started off with, right? And so this is pretty simple. We just end up rewriting the star equation that we just have right above. We're going to have Vf squared is equal to V initial squared plus Q naught 2m pi epsilon naught. And now we have 1 over d minus 1 over 2d. Right, so if you clean this up, you're going to end up with a 1 over 2d. And substituting that all back in, oh, and I'm for sure going to run out of space. Maybe. Okay, I'm going to start writing sideways here so we don't totally run out of space. If we clean this up, we're going to find, and take the square root, obviously, because we want to isolate Vf. We're going to find Vf is equal to V initial squared plus Q naught over 4m, now with a d, pi epsilon naught. Okay, and this is all going to be to the power of 1/2 because we're taking the square root. If you sub in numbers, you will find a Vf equal to 3.8 times 10 to the 6 meters per second. Okay, that's your final velocity. All right, so that's part A. Now what about part B? What do we want to find in part B? In part B, what is the positron's speed when it's very far away from the alpha particle, right? So we want to find the positron speed as our, here, maybe I'll label it, so as d goes to infinity, right? We want to find how fast is this thing moving when it's very, very far away from the alpha particle. Well, all we have to do in this case is go back to our star equation and set d to infinity. So what happens if we go back to the star equation and set d to infinity? Well, we end up with Vf squared equals Vi squared plus Q naught over 2m pi epsilon naught 1 over d minus, well, 1 over infinity is just going to end up giving us 0 in the limit, obviously. And so you just end up with this expression. We can clean this up. We'll just move the 1 over d over to here. I won't write another line to sort of do that simplification, but if you substitute in numbers at this point, you end up finding that Vf, obviously after doing your square root and so forth, you're going to end up finding that Vf is 4.4 times 10 to the 6 meters per second. Okay, so this is good. This is consistent. This thing continues to accelerate as it moves further and further away, and then when it's very, very far, it's going to approach this 4.4 times 10 to the 6 meters per second. Okay. Finally, in part C, so in part C, the textbook isn't super clear in its question. It says describe the subsequent motion if we change the sign of the charge on our positron. So basically change our positron to an electron. So I'm just going to take that to mean when does it come to rest. So we're just going to solve for when it comes to rest. They also talk about the kinetic energy afterward, but I'll just skip that. You can see it in the text if you want to. But basically, let's talk about where this thing is going to come to rest if we have the same initial setup, but if instead of a positron, we're dealing with an electron. So this thing has a negative charge, right? So what are we doing? We're letting Q naught go to negative Q naught, okay? And so we want to find where this thing comes to a stop. So if we want to find where this thing comes to a stop, we need the final velocity equal to 0, right? And we're going to solve for the d, the distance, the lowercase d, where this is true. Okay. So again, from the star equation, our Vf squared, well, that's going to be equal to 0 now because it's 0. but our star equation tells us that this is also equal to V initial squared plus Q now minus Q naught, right? Because we changed our Q naught to a minus Q naught over 2 m pi epsilon naught 1 over d minus 1 over the d that we're interested in. And now it's really just a matter of solving for that d that we're looking for, right? So to clean up the algebra, I'm just going to call this whole collection of constants a, just to make the calculation a little cleaner. If we do that, how am I doing on space here? Okay, we're fine. So then we're just going to change that to an a, and so what do we end up with? We end up with basically 0 is equal to v initial squared plus a over d, or no, wait, I should be careful about this. Let's clean this up a little further, because we're going to be, okay, so I'll just leave it like this and I'll do one more step. So we'll leave it like this, and a over small d, right? And so let's move some of this stuff over to the other side. We can move what we're sort of looking for over to the other side. So I'm going to add this to both sides. We're going to end up with a over d is equal to vi squared plus a over d. Now I'm going to multiply and divide by d here because we want to isolate our little d. And so if we clean this up properly, we're going to end up with a d is equal to a over v initial squared plus a over d, right? And at this point, you would just need to substitute in what our a was, so the thing gets a little messy, but it's not too bad. We're going to have a q minus q naught over, maybe I shouldn't have drawn that so big, but over 2 m pi epsilon naught. This is all going to be over v initial squared plus this a again over d, so we're going to end up with a q naught over 2 pi epsilon naught. There's an m there also that I forgot, and then this is all over our big D, right? And so, yeah, I mean, you could also just write it like this and clean it up one step. Just move the D up, and you'll end up with an expression that looks like that. And so if you clean this whole thing up, you stick in numbers for all these things. We know what all these are. We know what m is. We know what both of these q's are, q and q naught. We're going to take the negative q naught now. We know what the initial d was. We know what epsilon naught was. So if you do all this, you're going to end up finding a d equal to 9 point, or just, let's call it just 9 times 10 to the minus 10 meters. Okay, so this is the distance at which this thing is going to come to a stop if it's an electron, not a positron, and it starts off with the same initial conditions that we had above. Okay, so that's that one. I have another, so we have a small discussion here, and then another example that I want to do, but again, I'm going to pause the video before I lose this, so give me 1 second, and we'll get right back to it. Okay, so now let's move on. So now, what if we were interested in electric potential energy with several point charges? So we talked about sort of how this would look with 1 point charge. We talked about how if our test charge was moving through the electric field of another point charge, even though the electric field isn't uniform, we can define a potential energy, and this potential energy is only going to depend on the radius, like the distance that this test particle is from our other particle. And this is great because this kind of tells us that we're dealing with a conservative force here, and so we are justified in defining this potential energy and so forth. But what happens if we have multiple point charges, several point charges? Well, we've already seen this principle of superposition allows us to write down the electric field for all these point charges, right? We've seen that we can kind of just add up all the different little contributions from all the particles to give us an electric field at any point that we would like. So we can just, this kind of leads us to the conclusion that we should be able to write down the potential energy in a similar way, and that's exactly what we can do. So we can see the expression here for the potential energy associated with a particle in the electric field generated by a number of other particles, and you can kind of see how you would build that here. It would basically just be the sum of all the contributions from all the other particles, right? and we can see that here. So again, here in the notes, I bring up this point that that we define our potential to be zero at infinity here, and this is kind of what we did in the previous problem where we were looking at it, right? As our positron was getting out to very, very far away, we were setting that potential energy to zero, and so we're going to do a similar sort of thing here. Okay, so let's take a look. Let's take a look at one more equation, and then we have an example to take a look at. So let's say we start off with some number of charges. Okay, and we're going to be looking at the electric potential energy associated with assembling a huge collection or any collection of point charges. So let's say we start off with some number, call it some number n of charges q sub n. So it's going to be like charge q sub 1, q sub 2, all the way up to q sub n, however many we want, right? And we start off with all these particles infinitely far apart from each other, okay? And then we bring them all closer together. We bring them all close together such that the distance between any two particles, qi and qj, is given by this rij. This is the magnitude of the vector that would be drawn between the two of them, right? So our rij just defines the distance between qi and qj, okay? Then we can write the total potential energy for the sum of all these particles put together. So the sum of the potential energies in this potentially macroscopic object made up of all these point charges. And so the way we do that is to sum over all the individual pairs, right? And that's what this sum is doing here. So what are we saying? We're saying that the electric potential energy associated with assembling this collection of particles is equal to 1 over 4 pi epsilon naught times the sum of each qi qj over the distance between the two of them. Okay, and now we want to make sure we're not double counting, and that's kind of what this sum is doing. So if you think about how this would work, and we're going to look at it in the example below, but basically how this would work is we're going to sum over each pair without ever double counting. Like, we're not going to look at q1 and q1 here, because that would be, there is only one q1, so there's no distance between q1 and itself, so you would never look at that value. And as we go through this, we're not going to look at q1, q2, and q2, q1. We only want to look at q1, q2, and then q1, q3, q1, q4, q1, q5, and then q2, q3, q2, q4, q2, q5, and so forth, right? So never double count, never count with itself, right? So that's basically what this sum is doing. It's going through, adding up all the contributions that we get from each pair with each other one, okay? And so let's take a look at an example that will hopefully bring this into clearer focus here. So we have example 23.2 from the text. And so what are we looking at here? We're looking at 2 point charges, which are fixed in the positions on the x-axis. We see the drawing down here. So we have one charge fixed at the origin. Okay, that's going to be our q1. It has a charge of negative e. Then we have a second charge, which is fixed at x equals a, and this is going to be our q2. It has a charge of plus e. Okay, and we have a third charge. This third charge is going to be brought in from infinity. We're going to bring this charge in. It's a charge of plus e. We're going to call it q3. It's brought in from infinity, and it comes to rest here at x equals 2a. Okay, and we want to answer some questions about this. So first we want to find the work that must have been done by an external force to bring that third particle, that q3, which has a charge of plus e, from infinity to the position x is equal to 2a. Okay, so let's start off with that, and then we'll look at part B. Okay, so for part A, we know that, well, okay, let's start off. Okay, so we know that the work done to bring q3 from infinity is going to be done by this external force, and we know how to write down our work in terms of potential energy, right? So if we think back to the equations we just have above, we can write it down like this, right? So this is our work is equal to the negative of the change in the potential energy, and this is just minus ub minus UA. So the negative of this change in potential energy, right? But we're starting off, this particle starts off at infinity, right? So let's set infinity to be our zero potential, and so this is going to be zero. Okay, we're starting off way out at infinity. This thing has no potential energy out there. Then we're dragging it in. We're doing all this work. Imagine we're the external force. We're dragging this thing in all the way until it sits right next to the other two particles. Okay, so we have an expression that looks like this, right? And now we just need to solve for what is the potential energy of this particle sitting at that point. Well, let's do that. The potential energy of the particle sitting at that point is going to be given by this this expression that we have right here, right? So we can just go through and kind of add up those contributions. So we're going to have a 1 4 pi epsilon naught, and then our first term is simply going to be, well, we have to consider the first pairing. So what can we pair with Q3? Well, we can pair Q1 with Q3, and that'll have a contribution that'll go like Q1 times Q3 over R13, and R13 again is the distance between 1 and 3. And then we can also consider the pairing Q2 Q3, right? And this will be over R23. And now we just need to substitute in what some of these values are. We can see from the diagram what some of these are going to be. We can see what these distances are, right? The distance between Q1 and Q3, well, that's going to be 2a. The distance between Q2 and Q3, well, that's just going to be a. And so we can start subbing these things in. We know what the charges are. We know that Q1 is minus E, Q2 is E, and Q3 is E. So let's start subbing these things in. We're going to end up with 1 over 4 pi epsilon naught. And then we're going to have, so we're going to have minus E, E plus EE over 2A, A. Okay? And so why is that? Well, because we have a negative Q for Q1, but our Q2 and Q3 are both just positive E's, and then these are distances R13 and R23, right? We can clean this up. I'll do it a little bit over here, save some space. And so we can clean this up. Like I said, we're going to end up with an expression that looks like this. I'll factor out 2 factors of E here, so we'll have E squared. I'm going to pull out an A from the basement here, and we're going to end up with a 4 pi epsilon naught A. And if we do that, we're going to end up with a minus 1/2 plus 1. And so this is just going to give us a half. And we're going to end up finding that the work done, again, we're just calculating the work done here. This is just going to be equal to E squared over 8A pi epsilon naught. Okay, and so that's our answer for part A. That's how much work this external force would have done to bring the particle from infinity and sit it down right next to the two of these in the position shown in our diagram above. Right. Now in part B, we want to find the total potential energy of the system of 3 charges. Right. So how do we find the total potential energy of the system of 3 charges? Well, we just talked about that in equation 13 here, right? We're just going to have to add up all the contributions from all the interactions of our 3 particles here, and that's going to give us our total potential energy, right? So let's do that here. So what is our U going to be? Well, our U is going to be 1 over 4 pi epsilon naught. This is going to be the sum for I greater than J of Qi, Qj over Rij. Okay, that's just the equation from above. And what does this mean, really? Well, this means that we need to look at each of them. So we're going to have 1 over 4 pi epsilon naught, and now look at each pairing. We have Q1 and Q2 can be paired. That'll be R12. Plus Q1 and Q3 can be paired. That'll be R13. Plus Q2, and Q3, R23. Okay, those are all the possible pairings without double counting or without counting with itself, right? And so this is pretty simple now. We can just clean this up again. All these R's will have values in terms of A, so the distance from 1 to 2 is just A. This one is just 2a, this one is just a, and so forth. So I can clean this whole thing up, and it's going to end up looking like this. I'm going to, okay, well, I'll do it in 2 steps. 4 pi epsilon naught. We'll have a minus e and an e. These are our 3 terms. This will again be a minus e and an e, and this is just going to be 2 e's. This will be an a, this will be 2a, this will be a, right? And so we can factor out a bunch of this stuff. This is going to end up being e squared over 4 pi epsilon naught a, and we're going to be left with a minus 1 plus 1/2 plus 1, right? And so these will cancel out, and we're left with a factor of a half, and we are left with this expression. Oh, this should be a minus a half. Sorry. Right, because we had a minus sign up here. So we're going to be left with a minus e squared over 8a pi epsilon naught. Oh, sorry about that. Okay, so that is the answer to that one. Okay, that is the total potential energy in this system of particles, right? And so that's really it for this video. We're going to leave it there for now, and we'll pick it up in the next one with more on this topic.